I don't know if it worked out this way on purpose, but yeah, it seems like we're focusing on a few of the same things here. So a little reinforcement of the same message is never a bad thing that I've found in the industry, especially when we're dealing with something as important as joints and failures and just the chronic problems that we seem to have with various types of joints. So reinforcing the issue, um, explaining the problem. You can't really solve the problem if you don't know what the problem is. So that's some of the goal with some of the initial talks here, and I'm going to try to go into a little bit more depth. But also, I mean, what I'm talking about here is how to eliminate. I mean, that's important, I would say. Exciting, maybe a little bit optimistic for those in the room that maybe think that's a dubious statement. But I mean, the joints are where the issues are. I think if we took a poll here, you know, how many people here have seen failures in straight pieces of pipe, I'd say it's pretty low. I mean, it does happen from time to time if it truly is at the end of its life, but definitely more rare. Typically, you know, you're having issues, you're having them at the joint. So I hope to present knowledge that shows that much of the prevention of joint failures is actually just at the front end. There are things you can do when it's in service, because we don't want to just provide front end solutions, because a lot of you guys have things that are already running, already installed, already patched up. So we want to provide you solutions for how to eliminate those joint failures and make them a little bit more reliable for its useful service life. So just a little bit of the background. You're going to see, like I said, some of these things are reinforced where we're talking about the same joints over and over again that Jose talked a little bit about in his 101 presentation that Jeff talked about specifically with flanges. So there are several different types of pipe joining methods. Each are acceptable at times. That was sort of Jeff's probe question to Jose that I told him to hold off on. I mean, everything has its place, everything has its use. It's a matter of selecting the right use, the right time to use it, and also doing it well. Some shouldn't be accepted at all times. So these sort of two opposite statement here. Some are acceptable or all of them are acceptable at certain times, but some shouldn't be accepted at all times. It's critical to understand each joint and their pros and cons. So that is some of the background that we have to go into first here. Can issues be predicted? We get this question a lot. You know, we get pretty frequently, hey, what do you think about UT or what are some non-destructive methods that I can use in my miles of pipe on my plant site to predict the issues at every single joint? We get that a lot. They're useful tools, but the tools are only as good as the availability that you can use them on. If you have 1,000 joints in your system, are you doing UT non-destructive on every single joint? There's a lot more to that. You need to do a little bit more preventative, more engineering, more specification, more not allowing your pipe to shift 3 feet while it's in operation, because you know all the best non-destructive in the world isn't going to matter if you're skipping the first steps of specifications, proper engineering. So like I said, if you don't know what the problem is, you can't solve it. I'm an engineer, problem solver, so you can't really solve a problem if you can't identify what the problem is. So that's what we're trying to figure out here today, is education on joints, how they fail, what leads to the failures, and how to mitigate them, how to address them. First, we're going to lay out each primary joint style, explain them, list the pros and cons, then we'll talk about mitigation measures before a failure happens. You've already seen these, like I said, reinforcement. So socket adhesive, O-ring, bell and spigot, flanges, laminated. I say laminated because if you just say butt wrap, it sort of skips over fabricated branches where you have T's, branches, those types of joints. So anything really laminated falls into that category. So first, we're talking about socket adhesive joints. You know, you hear them called glue joints. That's what Jose was saying earlier. You have the bell and spigot ends. You can see sort of the image in the bottom right there of how it goes together with the male and female end. You have the bell end, and the spigot end fits in there, and you have an adhesive. But adhesive by itself is not good enough. There is surface preparation that goes into that. Now these are quick to assemble. That's why a lot of people like them. They are very, very strong in tension, as you can imagine. If they are done well, you try to pull that apart, and you're relying on that glue, that adhesive. So it is very strong in direct tension, but the success is very quality dependent. There's special tooling for bell and spigot joints that you can't just send somebody out to the field, scuff something up, glue it together, and expect to get a reliable joint. Weakened bending, I said it's very, very strong in tension. So if you don't have a lot of bending loads in your system, Go ahead, throw these in there as long as they're done well. But because there's no sort of external reinforcement, you're relying totally on that bond line. You can imagine how if you bend that pipe, you're going to start to weaken that adhesive line because there is no glass reinforcement creating that joint. You saw this picture before. You can see some torn glass. The light part is the torn glass there. So what would you say? About half of that got torn. So maybe you wanted full, you want 100%. So if we have half that, does that mean half the life? Maybe. If you wanted 20 years, maybe it's 10 years. Half the pressure? Well, okay, if you're operating at 100 psi, maybe that's only good to 50 psi now. Half the stress? Well, what allowable did you assume when you did your pipe stress with those joints? Did you assume 2,000? Well, maybe 1,000 would have been a lot more realistic if you're having a joint that's only 50% reliable. So generally speaking, we don't like shiny. Only if it's a finished product, we like shiny in FRP. But when we're doing joints, we want rough, we want torn fibers, we want to scuff the surface. So if you see a part that's failed and you see shininess, I don't know if you can see it very well, but there's a little bit of a sheen to that. So the inside of that bell right there, it's difficult to prepare well. So it might be prepared or should be prepared before it even gets to site and taped up. And if you just take the tape off or whatever and try to join it up, well, you're going to have that issue right there. You need to scuff it up again. There's special tooling to scuff it up to get a good profile so you can bond to that to increase the surface area, get the adhesive to bite. Very workmanship driven. You end up putting a lot of trust in your installers. I mean, you're forced to. You can inspect this, great. Inspect, 1,000 joints being put in. You can do that. There's a cost to that, sure. And Jeff said it's a little bit redundant at times, but if you have bad installers, you're putting a lot of trust in them to do 1,000 joints well 1,000 times. So that's very difficult to do. So they need to be properly trained to do these types of joints. Notice the sheen on this one. You don't see any torn glass fibers when this pipe's separated. Very common failure for socket joints. Another issue that can pop up with socket adhesive joints, you're going to see a little bit more probably on smaller diameter pipe where it creates more of an issue, is this one is actually a decent bond. But when you cut it away, you see all that adhesive buildup. They just smeared the adhesive in there. They stuck in the socket end and just squeezed out the adhesive to where it now reduces the ID quite a bit. So now you have flow issues, you have impingement points. So that's also another thing to pay attention to, is too much adhesive can be a bad thing as well. O-ring, bell, and spigot, somewhat similar to socket adhesive in that you have a bell and spigot end. The only difference is you are not gluing it. It is not a mechanical joint. It is simply just a sort of a friction fit where you have the O-rings that are creating that seal. So that allows that to slide in and out, which is, it's, Jose said earlier, good for buried pipe. It's common in cooling water pipe. That was actually my first job. That's what Miles is smiling at me right now, my first job. We walked down a cooling water pipe in 2006. Yeah, baby-faced. Yeah. So with these types of joints, you need axial restraint because you have, just like I said, free-flowing. There's not a mechanical joint there. It's not connected to each other. So when you think about let's say you have a cylinder with capped ends and you pressurize that, it's not going anywhere. It's balanced unless you have some sort of air in there, upset, whatever. But it's not going anywhere. Now, if you have only one capped end, one open end, you pressurize that, well, now you just created a rocket. So you have all that pressure thrust that's pushing against the one side. So at least with bell and spigot joints, it for the most part in your straight runs, it is just an open cylinder on both ends. So you pressurize it, theoretically, it should not be moving. At some point, that has to change directions though, right? So at some point, it's going to elbow down, so now you have that rocket, so you do need to restrain that part. But it's also good just to restrain each individual part so you can predict the expansion to go both ways, so you're not overextending one side and potentially pulling out. So it's a very specialty type of joint, but it is used occasionally. Getting into the laminated joints, aka butt wrap, butt joint, you'll hear just weld, very common, joint, overlay. All those are are all synonymous. So you butt them together and you weld. The only difference is there's a secondary bond bridging the gap. So when obviously steel, you're just welding the gap. Well, we still have that gap with FRP when we're butting them together, but we need to overlay it and join it together. So you're bridging that gap. So It's a very strong joint. It is very labor intensive. So labor intensive equals higher installation cost. It's done in stages, especially when you have larger diameter equipment. You're doing a lot of stages. Sometimes you can have as little as 2 guys in your crew. Sometimes you have 4 or 5 per crew, depending on how big the joint is that you're making. But it is the highest bending strength of any joint. You get strength in all directions. More or less, it restores the original part, but actually then some. So you're bridging that gap. So right at that joint line, it's the joint is being replaced, but you're also reinforcing on the outside. So if that joint line is right there, well, you're reinforcing the part on the outside. So sometimes that does hide some ills of oversights in engineering, where you have a little bit more joint reinforcement at head joints, for example, or shell-to-shell joints, or bottom joints, where you might have a vacuum situation. So that actually helps to stiffen up the shell a little bit as well. So comparing this to socket adhesive joints, where there's no additional material being added, you can see how this is a much stronger joint. On larger diameter, you would actually go on the inside as well and laminate that as well to create the seal, but also to add some structural capacity to that. To show a little bit of the process, you can see, there's skill, very skill dependent on a lot of these joints. Pretty much any joint in FRP is skill dependent. But you align it together. You have alignment tabs on the part there where you're joining it together, and then you see the guy filling up the gap to create that bridge, because it's very hard to roll out against a gap. So you need to create a little bit, you need to fill up that gap so you can bridge across it. Something on grinding. Many of you have laminates in your plant where you see the edges sort of peeling up. That's not uncommon. It's not always a fatal flaw. Sometimes it's uglier than it is anything, but it could turn into something, and you don't always know just by looking at it. But you always want to grind beyond the widest layer that you are applying. If you don't do that, anything you put on unprepared area is just going to peel up over time. So you want to make sure that you're grinding definitely past the widest layer that you are applying, so you get a good bond and you don't get any edge peel on the outside of that laminate. So this is sort of your crew going on here. You got one guy at the table wetting out the layers, building the stack. So they're going to make patches on a table, usually 5 to 7 layers at a time. And then once he's done with that, fully saturated, he goes to the part. You got it on his release agent, the Mylar. He's going to stick it right where it needs to go. You want to overlap probably about 2 inches so you get good load transfer between adjacent patches. And then you'll have the guys just rolling the air out, and that creates a very good, strong joint. The length of the laminate is usually very forgiving. If you know anything about FRP properties and strengths of joints and secondary bond shear, the length is actually very, very forgiving. So that's why having a little bit of edge peel is usually not the end of the world for your joint, because there's usually minimum joint length, and it's usually very, very conservative for what the actual bond shear stress is. It's more important about the thickness and eliminating any type of peel or any type of bending. Quick note on thermoplastic joints. Here you're seeing a dual laminate construction. Most are familiar with thermoplastic joints on PVC or CPVC, where you have solvent cement. For other joints, you need to fuse or weld the plastic back together, just like you do with steel. So here we have just a small section of pipe. Couldn't be more than 20 feet or so. All those blue lines are hand welds. So how many do we count? 11 in a little short, 15, 20 foot of pipe. You have some guy welding it by hand. There are fusion methods, but a lot of these you have to do hand welds at some point. So if you have 50 to 100 spools on your project with 10, 11, 12 hand welds per spool, you can imagine how you can have some issues. I mean, these are where the issues start to arise. Is there's just a lot of handwork in here. There's just a lot of joints to do on piping. I'm going to talk a little bit more about comparing tanks to piping as far as inspections, where tanks seem to get the lion's share of the attention. They're critical assets, but the piping often gets overlooked, and then you get issues like this. So clearly there's a benefit to making sure welders are certified. And by the way, there is welder certification, whether it is for thermoplastic or whether it is for FRP. There's secondary bonder, laminator, welder certifications. There's all of that per ASME and AWS. So it's one thing in the shop, but what about field joints? I mean, you can control the shop environment even if you have 100 welds to do in the shop. I mean, it's controlled. You can move it around to make sure you're always welding in the right direction. You know, that's easiest to get a good weld on. Well, when you're in the field, it's a lot more challenging, right? You have environmentals to deal with, time constraints. Everything needs to go together quick. It's an unfamiliar environment for the welders. It's challenging positions at times. You know, there's a lot of things going on. In this particular job that these guys are working on, there's over 750 joints to be made in 21 days. And also there's 400 flange sets to be torqued up and retorqued up after hydro test in 21 days. So these guys are rushing to get work done, not sleeping in their own beds, in unfamiliar places, uncomfortable positions at times. Got to pay attention, got to use good guys, got to use certified guys. So this is what a bad joint looks like. If you get the arc across the spark testing machine, that means it's a bad joint. So it's great when you find that when the plastic is exposed and not in service yet, because you can come back and fix it. That's what you would have to do. If the joint fails in service, what are you left with? A lot of times they just throw an overwrap over it, just an FRP overwrap over it, right? Which is, you see a lot of overwraps in FRP, that's not that unusual. But if FRP alone could work for this service, you would not be using dual laminate, you wouldn't have a thermoplastic liner. The thermoplastic liner is being used here because the FRP can't handle it. So you have something leaking and you're just gonna overwrap it with FRP, well, the FRP is going to get corroded. The FRP is going to leak. So, and anytime you're trying to repair welds that have been in service, thermoplastic welds, it is a challenge. It's never going to be as good as the original part. So very, very critical to use good vendors who know what they're doing. Most common failure is a poor bond, poor grinding, poor surface prep. Maybe it gets contaminated. Maybe you're working in humid environments. But things like laminated joints around T's, fabricated branches, they're prone to overstress. They're just large structural discontinuities. You have a big hole in the pipe, so it's just a natural stress riser. So, it's not uncommon to see underbuilt T's, poor engineering where a lot of the stress is realized at these joints, and also in cases maybe you have pressure surges. That's pretty common too. It shouldn't be, but yeah, a lot of times we have failures like this where you actually see torn fibers. That's not a bad joint necessarily. That was exposed to an extremely large force to be able to break that. The one on the left, I mean, you're squirting out water. That looks like a poor bond. It's very, very thin laminate. The one on the right, I mean, all that torn fiber, that's a lot of energy that it takes to break that apart. So that was a pressure surge on that one, coupled with some poor engineering. Flanges, last but not least. Okay, seems like I'm always talking about flanges. I can't get away from it. I'm usually known as the guy who hates expansion joints. But if there were actually flange guys here making them, they think I was like public enemy number one talking about flanges, just because there's so many issues with flanges, but there's not enough education about why that is, what goes into flanges that creates such an issue. It's not just, it is torque procedures, but it's not just torque procedures. It is construction of the flange, but it's not just construction of the flange. It's selection of the flange, it's selection of the gasket. So many different variables here. So if you understand them, you can at least start to whittle down the potential variables to the things that you can control. So flange is quick to assemble. If you're comparing quick to assemble to butt joints, yes, you can do flanges quicker. To socket adhesive joints, maybe not so much. Very, very costly, increases the leak potential. We know that's susceptible to cracking. Everybody has seen issues with their flanges cracking, unfortunately. So two main styles, just to, again, reiterate, full face, where you have the bolt holes, we're held to class 150 drillings. And then the other one is a lap joint flange or Vanstone flange where the bolt holes are excluded. The pros and cons, I would say, to the flat face here is it's generally easy to assemble. People are pretty used to doing flange connections. It's a common flange, so they know what they're getting with a full face flange, at least in terms of bolting it up. The cons, I can't stress this enough, do not mate it to a raised face flange without having a spacer ring to fill up that gap. It requires more bolt torque to seal the gasket. Jeff talked about it a few times. The bigger the gasket, the more area, so the more torque it takes to seat the gasket. So if you can reduce that area with a lap joint flange, then you can use the same torque and create more sealing stress on that one. Now, there are obviously torque issues, there's fabrication issues, but I want to let you in a little secret. We, and I'm not saying we Maverick, the FRP industry doesn't really know exactly how to accurately analyze flanges. And that's just the truth. We have steel approaches that we have modified, somebody way back when, decades ago, has modified to use for FRP flanges. However, there's a bunch of different factors. You look through the flange design equations and calculations, you're gonna be like, well, I don't know what any of these factors mean. I'm trusting that they're right, and that's sort of what we do. That is what we at Maverick do when we're sizing the flanges. So we can come up with the thickness required, right? It's very geometrical when you're doing the flange calculation, but then you're getting into the actual fabrication of the flange, how you're layering the layers, how you're alternating the layers, reinforcing the hub. All that goes into making the flange work. But there's still design aspects that's a little bit of a black hole that we're trying to work on in the industry. So the other thing that you get with full face flanges here is the need to spot face. And spot facing can be a problem because we are held, for the most part, to Class 150 drilling patterns. Can't really change, so we're forced to conform almost always. Well, if you have high pressure flanges, most FRP is ID driven. So you set the ID, you build it out with the thickness. So if you have high pressures, you need thicker components. So now you just pushed out the OD a little bit more. You have thick corrosion barriers, like 100 mil, 0.1 inch corrosion barrier is pretty common, but more aggressive services, you're going 200 mil, 250 mil, 500 mil. So now that's pushing everything out a bit more. So now you build the flange on top of something with a 1/2 inch thick corrosion barrier. So now we're getting closer to the bolt holes. Dual laminate construction is the same way, where they have their set ID and we're building on top of that. All of these are pushing out the bolt holes. It's just a geometric issue. We cannot get around it. So we have to actually spot face in certain issues. It's what is the threshold for the permissible spot face. So speaking of flanges, we don't know how to accurately analyze lap joints are next on the list. At least there's a calculation approach for full face flanges. There's not currently for lap joint flanges. We are working on it in the ASME committees, but we are not there yet. So a lot of it is just testing based, but there has been a lot of success with lap joint flanges. It's just we don't really have a very good calculation method right now. But you can mate these to raised face flanges. They are self-aligning. You don't have to worry about two-holing. That's a very nice aspect of it. And it's reducing that area where you have the loose FRP stub with the loose backing ring, and you have a smaller area where you're inside the bolt holes now instead of all the way to the OD of the flange. So you about halve the area, so the same amount of torque, you get double the compression on that gasket. Not as prone to overstress because it's not as big a moment arm. If you have a flange with bolt holes out here, that's a pretty big moment arm. If you can reduce that a little bit, then you have a lower moment arm, lower stress when you're torquing that up just because the stub is a smaller OD. The cons, it's not a huge con, but it does require a steel composite or composite backing ring, but a lot more pros than cons. So to me, why not always use lap joints? That's sort of where I'm going right now with my recommendations is use a lap joint where you can. I'm sure there are places where it doesn't really work, but use it where you can. All right, so nobody's had issues with leaking on flanges, so I can just skip past this. It's a mechanical connection. You have dissimilar materials, varying strengths, varying flexibilities. You have FRP, you have steel hardware, you have soft gasket, you have bending on the flange, you have pressure, you have temperature fluctuations, you have creep, you have fatigue, you have things moving 3 feet back and forth. All of these go into why we have leaks at flanges. So most commonly we'll say it occurs due to under torque or just improper torque procedures. Especially with a full face flange, you are concentrating that torque right around that bolt hole, right? We're assuming that it sort of distributes all the way around the flange evenly. But if you do, look at Fujifilm on gasket compression, it's very, very focused around those bolt holes. So if you're cranking down one bolt at a time and then going to the next bolt, you're putting a lot of focus on that one area, then you're going to go to the next one. So you want to do that crisscross pattern and go in certain increments so you're not just torquing to 100% at the same time. If gaskets are soft, in non-metallics, we love soft gaskets, easy to seal. We don't want to break our flanges, but those are more susceptible to creep, cold flow, which causes a loss in pretension. Now, if gaskets are hard, they're much higher torque values are needed to seat those gaskets. That's where lap joints would come in handy. But in some cases, those high torque values are now going to result in overstressing your flange. So what do? You want the benefit of a hard gasket, or maybe the PTFE, which is a hard gasket, I guess I should say. But the torque to seal that PTFE might overstress your flange. So you're sort of in a predicament there. Not every plant requires torque wrenches. That's a shame. How many observe the bolt up? Your example was great. Like when I heard that, I was like, holy cow, like there's somebody doing that. But for the most part, it's a lot of cowboys out there that are just going out there and, they need to bolt up the flanges. They need to do it quick, but we don't, we're trusting that you do it right. So it could be from under-designed or poorly built flanges for sure. It is not just, I don't want to, blame the installers. There are things, and a couple slides later, I think I'm going to show the potential issues with construction of flanges that, if overlooked, could create these cracked flanges as well. Just like T's, these are natural areas of stress concentrations, just discontinuities that create natural stress risers that need to be paid attention to when you're torquing and also designed. So you could do everything right. Torques are good, gaskets correct, but you could still have issues if things are overlooked. So you need to pay attention to what you're bolting up against and act accordingly. So steel flanges and valves often have the raised face. So if you're putting a full face flange on there and you torque it up, you end up cracking the flange. So that would be a case where you need a spacer ring to fill up that raised face, or just use a lap joint flange on that. Honestly, the lap joint flanges are superior. I'll say that again. But like I said, if not, you have to use a spacer. So we have the background complete, but without that knowledge, you can't go anywhere. You can't really proceed to the next step if you don't have that background knowledge of how the different types of joints, the pros and cons of each, where they're used, where they shouldn't be used. But there are several tangible preventative measures and solutions that we can introduce for eliminating leaks and failures. So some are preventative. I'll say that before a single part is made. But like I said, you guys have things that are already in operation. You want to address the issues or potential issues, potential reliability issues on everything that's already installed. So I want to provide some solutions for that as well. Stick with flanges first. Look at alternative flange styles. Lap joint, but there's also a style that's not used as much, a little more common on larger diameters, with a full face where you machine a groove in the face of the flange where you can put an O-ring gasket in the flange. A lot of the benefit of the rib gaskets that you see, where you're focusing a lot of that load just on a smaller area. So load over a smaller area means higher stress, so you can get that seating stress with a lower torque. So those types of flanges are great for reducing leaks. So if you want to avoid leaks like this, I mean, these are just inarguable. Lubricate the threads so you can have some prediction of torque, so you're actually pre-tensioning it well. Use a torque wrench. I mean, yeah, not the cheater bar, not your arm. We hear a lot where they torque to the first crack, and that's how they know that it's sealed. Well, you've already broken your flange. Retorque after a period of time. I get it. It's hard. It's hard to come back a day later. It's hard to come back a week later, a year later to retorque your flanges. They're up in racks. It is hard, but these are connections that do not last forever. The gasket material will soften. You're going to lose your pretension. So these first four, I mean, they should be 100%. If your system cycles significantly, that's that periodic retorquing I'm talking about. Again, consider using lap joint flanges. What are you guys getting out of this? Use lap joint flanges where you can. So how much are you paying attention? Are you just blindly trusting your installers? What are you demanding in your specs? What oversight are you providing? Do you have oversight in the shop when they're building flanges? Do you have oversight when they're installing? Do you have any QC forms? Do you have people initialing which flanges they're doing and what torque? What's their target torque? What's their torque, their bolt pattern, their sequence? You can demand all of that. You want to know the technician that made it, the date that they made it, what torque were they trying to get to? And if they sign off on that flange, I can guarantee they're going to pay a little bit better attention to what they're doing for torque up. A flange may look great on the outside, but if you are not specifying them right, who knows what you'll get. Maybe you'll just get a lot of filler putty. Does that show up very well back there? We need some more brightness. A lot of filler putty in that flange, not a lot of glass reinforcements. This one in the middle, you have a lot of just random glass sort of shoved in there. Where the one on the right, that's how a flange should be built, where you have rings versus risers. So this illustration here is basically showing how a flange should be made where you're alternating the glass layers, where this is called a ring layer that's just building up the flange thickness, and we call that a riser where you're building up the nozzle neck and having directional glass through the hub. That is critical. So you can see how the flange face and neck are constructed integrally. If you buy the flanges on the left, flange failures are much harder to prevent. Also, a little known secret, there is no ASTM or ASME standard that we use in the industry that says you have to build a flange like that. So that's on you guys right now until we fix that. We're working on fixing it, but that's on you guys to make sure that you're specifying how flanges are to be made. Otherwise, you can just get flanges that are made really quick and they look great on the outside, and once it's made, you can't do anything about it. Again, certifications exist. Not everyone is aware. I just had this conversation with somebody last week. When I told them about bonder certifications per ASME RTP1, they're like, what? There is such a thing? Yes, they exist in RTP1 for tanks and NM2 for pipe. You can do it for laminators, you can do it for bonders, you can do it for thermoplastic welders. This is the actual step of certifying bonders per RTP1. So basically, they make a straight piece of pipe, they cut it, they join it back together, and then they cut it again. So now we have the joint on the outside, but there's a little bit of lip in there to where when we put it in a machine and we load it up, it's focused on that joint itself. So we can calculate that exact area of the bond area, and we use a machine where we obviously have a load that we can determine. So we have the exact bond strength, and if you have to get it over a certain amount of times to be certified as a secondary bonder. Hopefully you can see it well. Look at the bottom right here. I'm not sure. Yeah. So that's the test. You saw it sort of bottom out there where we failed it at a certain load. And, like I said, we have that area. We know that bond strength. So that is the certification for secondary bonders per RTP1. So ways to improve reliability during fabrication. Ideally, you want to get inside to seal, but you cannot always get inside to seal the cut edges. So what do you do on small diameter pipe? What do you do for aggressive surfaces where you don't just want the cut edge being exposed to the surface? So ideally, you do what's called a wrap cap or a drape cap, where you have at least a veil, we would say. Some just resin coated, but at least a veil, maybe a mat too. If you go too thick, then you start to get that impingement point on the inside, so maybe that's not ideal on small diameter. But the idea is to protect the cut edges, because if the fluid touches the cut edge, that's where glass is exposed. Fluid gets to the structural layers, and now it's starting to wick in, migrate into the material. So that's how you can have some joint failures there. So maybe you don't want to decrease the ID. So like I said, on small diameters, that can be challenging to do anyways to get it on the inside. So you can just do an edge cap where you just put a veil on the edge. That is not as good because you do have loose edges that you're not going to get down perfectly on the edges, on the cut edges. So there usually is a little bit of fluid that can get up behind that. So that's not as good as the wrap cap, but it's better than nothing. Or you can try to eliminate the cut edge completely and just make it as integral a joint as you can, where you actually taper grind back the pipe at where they come together and basically fill in that joint with laminate to create a more of an integral pipe there. Okay, so yeah, you did your front end prep. You have your torque procedures. You have good specs for building the flanges. You selected the right joints. You did all your engineering. You've done all that, and you still have issues. Well, I mean, some of them just have engineering problems where in these pictures, what you're seeing here, what I'm trying to show is you see sort of an earthworm type thing where you're seeing a bunch of overwraps on socket adhesive joints. So there are owners, and I'm not opposed to this, who are like, okay, you want to do a socket adhesive joint? I'm good with that. It's quicker to install, but I also want you to overwrap it so we get the benefit of the laminated joint. So that's not a problem. That's belt and suspenders. That's actually a pretty good, strong, reliable joint. But when I go into a plant and I see a bunch of earthworm and overwraps on random fittings, random elbows and tees, evidence of leaking on flanges, my mind usually goes to engineering problems if you're seeing a lot of overwraps on your pipe. It tells me you're dealing with nuisance leaks, and I think it's engineering related. Socket joint, I mean, there's no shine. I mean, this thing broke pretty clean, but you can see some glass fibers there. So, I mean, that takes a large load to break that. So to me, that's a stress issue. I mean, you can overwrap these joints, but to break a pipe, I mean, that takes a lot of load because we're dealing with design factors 5 to 1, 6 to 1, 10 to 1. So to break it, that's 5, 6, 10 times the load that you thought was actually going to be on component. So that takes a lot of load. So just overwrapping that sucker is not going to do a whole lot. So if you have pipe that's walking, you have engineering issues, or at least supports that are walking, because you don't have enough restraint in your system. So all that force going back and forth is just being realized at the joints that can end up breaking them. So brief awareness about the properties. This is a slide comparing thermal expansion coefficients between FRP. So we have the type 1, type 2. Jose explained that. That's all mat for type 1 and alternating mat and woven roving for the type 2. In the middle, you have the 55-degree filament wound pipe, and you can see it compared to carbon steel. So at its worst, around type 1, that's about 3 times the CTE. So for steel guys, I mean, 300 delta T from 70 would be at 370 degrees. But we get that same amount of expansion at delta T of 100 at 170 degrees. So a lot of people look at 150, 160, 170 and like, well, that's not too high of a temperature. I can analyze that, or we don't need to analyze. We can do it by rules. But we have the same amount of expansion as the steel guys do with something running at 370 degrees. So we need to control that expansion to protect the fittings. The other drawback of FRP is you don't have a yield point. The yield point is the break point. You have no warning, very low elongation prior to failure. Could be lower for different resins, but somewhat, less than 4% is about where we are for resins, but that goes down even more when we're making the actual laminates. So we need to stay away from this point. That's what the design factors are for. We need to stay well away from this point because there is no warning before something's going to fail. So can issues be predicted? In the sense of knowing where hotspots are in the system, I mean, yes, do stress analysis. Where are your hotspots in the system? A well-done pipe stress is going to tell you where the hotspots are. If at all possible, is it possible to move joints around in your system, whether it's a field joint, where your flanges are, to get away from where the hotspots are? Sometimes you can't. If you're at a T, if you're at an elbow, I get that. But maybe in a hot spot on an elbow, maybe that's not a good place for a socket adhesive joint, or maybe that's a place you want to overwrap that socket adhesive joint. So those are the different considerations that you gain by doing a pipe stress analysis. Use certified bonders, people who specialize in FRP, not just guys from the local hall that don't know anything about FRP. They can't even spell FRP. So in the sense of predicting failure, there isn't one tool that's out there that works perfectly. I mean, there's just a lot of joints in the system. You cannot check every single joint. I mean, the magnitude of the stress plays a part. A lot of non-destructive UT might just look at pipe. I'm telling you, your pipe is good for 10, 15 more years. I mean, that's great knowledge, but what about all my joints in the system? So the tool that we now we currently have the most confidence in as far as in-service solutions in figuring out where the joint is at is using infrared. So thermal imaging, your system has to be running. Okay, so systems running aren't a bad thing because we can also see leaks, we can see movement, we can see things going on. So we want hot on the inside of your pipe so we can get a reading on the outside. So we'll look at the joints. I mean, we're not quite at the point of predicting failure or remaining strength and thickness. There's theories out there that we can actually back calculate thickness of that joint, the remaining joint, based on the temperature we're reading. If we knew some more variables about the part, about the construction, that we're working on a little bit in-house as we have with all the free time we have. That's some of the research that we're looking at. But it is really helpful in finding the hot spots to improve the knowledge. It allows you to be proactive, to know, okay, I got to pay a little bit more attention to that. Or maybe now I use my UT. I'm seeing a hot spot there, so now I actually use my UT and actually measure the thickness of that to see if I'm at all in an area of concern. So that's what we're currently recommending for in-service solutions, to be able to find those hot spots and then overwrap them as sort of a preventative measure. So final thoughts, I mean, hopefully I've hammered it home. Before a single part is made, you have a lot of decisions to make. Consider your options on joints. Make sure you have good specs. Are you able to move any sort of joints around to avoid some of the hot spots in your system? What flange style do you want to use? Can you use lap joints anywhere, or are you forced to use full face? Do gasket selection. Calculate your torque range. All these things are done front end. I mean, you're doing your pipe stress analysis ideally where you do the correct support system. So we are eliminating all these potential variables as much as we can up front, so we can at least say that's not the issue. Jeff made that point earlier. It's like there was good installers, so you could at least say anecdotally, my guess is that's the least likely scenario, right? So get as many of those as you can that are the least likely scenarios, so then you can focus on the ones that are a little bit more variable, like field installation. Hard specify the things that are important for you, your owner, to protect you, protect the personnel. System engineering, analyze almost everything FRP. That's what I say. I know there's some milder services, but for the most part, we're dealing in heavy corrosion, heavy high temperature. You want to be doing stress analysis on that. Use quality manufacturers, installers. I can't stress this one enough either. Use guys that know what they're doing with FRP. Don't just trust that they know what they're doing, because more often than not, it seems that they don't. So use guys that are trusted, but have them confirm it to you. Have them verify that trust. Don't just say, yeah, we got it, we know what we're doing. Have them explain it to you. What is their process? What have they dealt with this before? What are their solutions? That gives you at least an idea that they've dealt with this before. This is not new to them. They know what they're doing. But don't assume that FRP can't be learned. Don't just blindly trust, but you don't have to be an expert, though. I mean, it's all about who you know, right? You just have to know the expert. But the more you individually learn about FRP, the more you are in control of your systems. You're going to increase your safety, increase your reliability, and you're not just putting your trust in other people. So failures don't have to be accepted. I see that too much, where it's like, it just leaks. We just have a crew on standby that's just going to patch it up when it leaks. You don't have to accept that and just deal with FRP like that. All of these things can be prevented and have a reliable system. So thank you for your attention. I knew I had a little bit extra time, so I used up a little bit more. Yeah. So any questions?